Okay, thank you very much for your patience. We have our third speaker, Dr. Marcello Puligheddu, who will be presenting on acceleration of electronic structure codes on heterogeneous hardware. The podium is yours, Doctor.
Okay, hi. Thank you. Can you hear me? Is mic okay? Okay. Let me try. Okay, so that's laser, and that's next. Okay. So start to talk a bit about ab initio electronic structure code. I think some of you are already familiar with what I mean by this, but essentially what they do is the computer property of a given system under study from first principle. We essentially simulate all the atoms and electrons in our molecule or crystal or however you want to call this system. The idea is they give us quite detailed insight into physical and chemical properties of molecule and solid, and depending on your level of theory and how much computational power you want to spend, they can usually be reliable. And they are used for modeling and design of different materials, so batteries, solar cell, pharmaceutical. We saw a lot of examples in the poster session yesterday. Our work is focused on two of these programs, CP2K and Crystal. Now, okay, so a bit of details about how they look under the hood. So we want to study our system, and the idea is the state of the system is given by the solution of this equation, the Rutham equation. Oh, strange. So essentially, it's a generalized eigenvalue problem between our Consham or Fock matrix F, our our molecular orbital energies, and then we have the overlap and density matrix. And now, this program can be quite complicated with many different steps. Let's say that the majority of the computational work in this course consists of these two essential steps: the diagonalization of the Consham matrix F to obtain the new density matrix C, and then from the density matrix C and other information, we need to form the new Consham matrix F. And then these steps are repeated from an initial guess into a cell-consistent field procedure until we are confident we reach convergence, and we can then compute the properties of our material. Of course, now, this first step is the diagonalization of a matrix. It can be dense, it can be a sparse matrix, it can even not be a metric and just be a general linear operator. And okay. And then step two, which is the focus of my work, is essentially a complicated step, and what it does is requires the evaluation of a truly enormous. Before screening, it should go as the number of atoms, electrons, the number of states, generally speaking, in your system to the power of 4. So you can imagine this number grows quite quickly. Number of electron repulsion integral. More on that on the next slide. And the idea is these calculations are very expensive. They account for quite a large fraction of most HPC systems. And what we want to do is see if we can make these calculations more affordable by exploiting the computational power of GPUs. So now, my work will focus on the contribution to the Consham matrix coming from the exact Hartree-Fock exchange. So essentially, we compute this four-center two-electron integral IJKL between four different basis functions in two different variables, x and x prime, with a Coulomb kernel inside the integral. Once we compute this electron repulsion integral, their contribution to the Consham matrix comes from their essentially tensor product with an exchange with the density matrix, and then goes into the Fock matrix. in our code, CP2K and Crystal, these these basic functions are Gaussian orbitals, so they contain a radial function, the spherical harmonics, and then of course a Gaussian function. And they look at your classical atomic orbitals you see in any chemistry textbooks. And then an actual basic function is a linear combination contracted on these primitives. Now, we need to compute an enormous number of these integrals, and as you saw from the equation before, they are also complicated. They are 6-dimensional integrals in x and x prime, plus you have the Coulomb term in the middle, complicating convergence quite a bit. Accelerating them on a GPU is not trivial. So even before starting writing any part of the code, we just ask ourselves, what is the best approach to the efficient calculation of GPU? There are quite many different resolution identity, Obara-Saika, MD mode, ND method, and other I'm not going to mention. How do we integrate it into existing codes? Those are oldish code, especially Crystal, and they are like hundreds of thousands of line of code. And of course, integration is not a simple problem. And then of course, we want to work on large systems, so we need to think about parallelizing our problem across multiple GPUs. So we started with the simpler possible process, and then we move our way up. So we start with a calculation of the much simpler overlap matrix, which is just a product of 2 basis functions instead of 4. Work on that. We try to keep the structure of the code flexible as much as possible. I have to say, before writing any actual CPU or CUDA code, we started with just simple, well, not simple, but just more simpler Python prototype of our various functions. This helps quite a lot. It's much simpler to transform a Python code than it is to transform any C or CUDA code. And then, of course, move our way to the force center to electron integrals running on multiple GPUs. And then, yeah, no free lunch. The routines that take more time are also the harder to accelerate using GPUs, but yeah, we knew that from the beginning. Now, actual calculation of the integrals. So, we choose to go through the Obara-Saika correlation with the Gordon-Pope method for the early contraction. So, very simple integral between S-type orbital can be done analytically, which is helpful. Integrals of higher moments can be built iteratively from these fundamental orbital and their sign derivatives. So as I said, we use the Obara-Saika vertical correlation and the Gordon-Pope method. For example, we can build integral between a p orbital and 3s orbital as a linear combination of the simplest orbital and its derivative. We repeatedly applies these, in this case, vertical operation and then other more complicated operations to increase the moment on the integral until we reach the angular moment that's needed from our basis set. It can get quite complicated. For example, computing an integral between 4D orbitals require 86 of these steps. Yes, so what we do is skipping quite some steps. We pre-compute a plan on execution, as in how do we go from this fundamental integral to these integrals. We pre-compute it on the CPU. We refine it essentially to increase the performance of our calculation. So we fuse operations that are similar, that can be done at the same time to reduce the number of steps. We can do a lot of pre-computation of stuff like memory offset, size of array, a few intermediate indices and stuff like that. So we do them once on the CPU, and then we can just read them as needed on the GPU. Of course, we identify transformation that can be done concurrently, extremely important on a GPU. So we only synchronize we only tell our GPU components to wait for a calculation to be done only when it's extremely necessary for correctness. Then, of course, okay, what we do is we start with this primitive Gaussian function, and then we contract them into the actual generalized contract basis set, which is used in these simulations. As I mentioned, we prepare this plan on the CPU, we save it, and then we run it on the GPU. What this means is that the control logic itself on the GPU is relatively simple. It's by no means trivial, but it's much simpler than manually building the integral and computing all this stuff. So what we do is we save it on the CPU. It's just a bunch of integer and pointers, and then move it on the GPU. The actual calculation is quite complicated. I'm not going to go through all the steps. It's just essentially starting from this simple integral, move all the way to the calculation of the full integral using the correct spherical harmonics. And then as a final step, the contraction between this integral and the density matrix to compute their contribution to the Fock matrix. A bit about the parallelization of this work. So we do it in steps. In this simplified is just 1, 2, 3, 4, 5, 6 steps. What we try to do is these steps can be parallelized on a GPU in different ways. So we take advantage of that. And for example, we fuse a split operation as needed to reach acceptable performance on the GPU. Yeah. So now, anyway, so I only described what is the innermost core of the calculation of the electronic repulsion integral. It's a bit of a simplified view because you have to consider that real integral are symmetric, as in you can do some permutation on the order of the atoms and get the same values. So we need to account for that to essentially skip some calculations when possible. They're done on the periodic boundary condition, and then they are screened, so it's essentially possible to estimate before even computing the integral if it's going to make a meaningful contribution, as if the integral is going to be larger than some cutoff of, I don't know, 10 to the minus 15 or something like that. In that case, we can skip it, which is very efficient on the CPU. It complicates the code quite a bit on the GPU and, yeah, limits efficiency a bit. And then, of course, the actual basis set is just a linear combination of this integral. It's a linear combination of Gaussian, so the actual integral are linear combination of these primitive integrals. Now, each integral is actually small. We can do them depending on the angular moment in nanosecond or fraction of a milliseconds for the larger one. So we have to do a lot of them, like millions even for a very simple system after screening. So how we pack this integral to expose parallelism on the GPU is just as important as how we compute them. And then, of course, yeah, I'm going to skip this. Essentially, we could use some intermediate values that can be computed before the actual integrals, but it complicates the code quite a bit. It complicates the data transfer quite a bit, so we actually don't think it's going to increase performance. Of course, we don't need the electronic repulsion integral themselves. They are just a nice intermediate step. What we need is their contraction. We do this contraction on the GPU, so we reduce memory transfer a lot, and it actually simplifies the code. We can do a lot more work in parallel. And then I talked already about integrating this library into already existing code. It's not a simple problem, because each code uses its own data structure to save both the density matrix and Fock metrics. So it's a problem, iterating over the integral we need to do from the density matrix, and then of course the contraction with the sparse density matrix, and then on into a sparse Fock matrix is an interesting problem on a GPU. There's quite a lot more about that, but that's for another time. I have some preliminary results, so this is just speed up on a i100 against one single core, so very serial code on a Xeon 5218. So I have the speed up as a function of the total angular moment, so each angular moment is, different integral, so anyway, different combination of integral. What we see is that it was kind of interesting that the speed up increased sharply after the zero moment, just because of the way we compute this integral. Then it's followed by a gradual decline with respect to the total moment. We think that honestly part of this behavior is just due to the limited number of integrals at higher moment, because it's quite clear that a lot of the speed up comes from being able to batch a large number of integral on the GPU, so they can be done concurrently, and essentially the GPU is always fed new work to complete. Yeah, so I think I'm going to skip that. Essentially it's about we can compute this integral for some system faster than we can prepare them, so we use OpenMP to essentially pack a lot of integral at the same time and alleviate this problem. So, moving to conclusion, we discussed the use of GPUs in local babyset ab initio electronic structure codes, CP2K and Crystal. We briefly discussed some of the way GPU can be used to accelerate this code, and some of the challenges in the calculation of the exact Fock exchange, and some preliminary results. So, this work was funded by the Excalibur project, a very large UK project, and my work in particular is part of this, particularly the exascale HPC branch. Those are people I need to thank, my line manager, Ian Bush, my boss, Gilberto, Ellen, and Tom, which is for their help. And these are conclusions again. Thanks for your attention.
Thank you very much.